Hey, differential equations class. This is Mr. Blevins. I'm going to go over Euler's method, and I'm going to talk about how to code it in Octave because we're just going to be short on time. So I want to make sure that you guys get to see it and be able to go back to it if need be, especially if you never coded in Octave before. So when we're doing Euler's method, we got to be given this. We talked about this in class. This is our differential equation. Remember now, the differential equation can have x's and y's. So that's all this is saying is your differential equation, your derivative is equal to something that has x's and y's interacting. Okay, the one that we did in class was y divided by 1 plus x squared. So that was the one that we'll use for this example too. All right, and then this notation that you'll see, this is saying the y value at the initial x coordinate you're given. It doesn't have to be 0. It's just x naught just means the initial value is equal to some initial y value. So x naught, y naught is just initial y value, initial point that's on the graph. So again, ours in this example is -3 and 1. Okay, so that's just an initial condition, the known point that's on y. Again, the thing that we're after is y equals some function of x, something to do with x. And again, they're not always functions, but this one will be. Okay, so what do we do with Euler's method? We're asked to estimate the y coordinate at some point that's not the initial point. So the initial point, again, that was x naught. This is x n, so this is just some other point. So you can also think of it as a and b if you're more familiar with that notation. A is the initial point that we're given, and we're making our way to B. All right. So this is Euler's method. We talked about it. We have the uniform step size. We're always moving in the x direction, the same value every time. But depending on what our differential equation spits out at these different points along the way, this can definitely be different. It can be positive, negative. It can change signs. So we can add, we could subtract to get our new y's. Alright, just notice the notation here. I is just some number. It's a number between 0 and n. Actually, it's a number between 0 and n minus 1. I did that in class today too. Because when we plug it into the very last one, the very last value, it can be, if it's n minus 1 and we add 1, we get yn, that last value that we want. So anyway, there's Euler's method. This in particular is the one that I want you to pay close attention to, because this is the one that they actually have to code. This is the one that we're after. All right, and then delta x that we see there, that's just, once again, we talked about that, the final value of x minus the initial value of x divided by n. It's the same notation that you used in calculus when you called them a and b's. So like the Riemann sums, b minus a over n. All right, let's go over to Octave and start coding this thing. All right, so we're given an initial point, and Octave, I like to use x naught and y naught. You can, like I said, you can use a and b, and it's fine. But I'm going to say x naught was our initial x coordinate, so that's -3. Okay, if I hit enter like we said before, it gives me a summary of what I just did, and I don't need that, so you can always use the semicolon to not see it. So the initial y value was 1, and again, I don't want to see it, so I'm going to hit semicolon. Okay, now we have to have an initial point. That's one of the things. We also have to have our initial differential equation. So we can call it whatever we want to. You can call it f. Sometimes I'll use f prime. You'll see me write that sometimes to remind us it's a derivative, but you can just call it f. F equals, so what we're going to do here is we're going to define an inline function. So f equals inline. I'm going to open a parentheses. I need an apostrophe to define the function. So what is our function? It is y divided by parentheses 1 plus x squared. Alright, so that is our inline function. Alright, I'm going to hit enter just so you can see it. So f is a function of x and y, and this is how we get the output of that. Alright, so if I type f of -3, 1, it gives me a number, so 1/10 like we saw in class. I can do it for any point though. I can say, all right, anything that would be defined. So f of 4, 2. So it's plugging 4 and 2 into the function and evaluating it. So once we've defined f, anytime we call f in this format, f of x coordinate, y coordinate, it'll give us that. But remember, what is f? F is our, let me go back over here real quick to remind you, f is our differential equation. Alright, so this is what f is. So it's the slopes of this thing. Alright, now I want to come up with a new y. What's the new y? Or sorry, new x and new y. So I've got my point. I've got my differential equation. I need delta x too. So I'm going to use delta x. We used 5 for that last value. So let's do, I'm going to call it dx for delta x. Delta x is parentheses my value for my final value for let me do it this way real quick. I'm going to call the final value xn. So the final value was 5. That's where I wanted to evaluate the y coordinate at. Alright, and now I can say delta x is equal to parentheses. I can literally write in xn minus x naught. Alright, oh, and I haven't defined n yet, sorry. In class we did from -3 to 5, which is 8, so n equals 8 steps. Alright, now finally I'm ready for delta x. So delta x is equal to b minus a over n, or in this case the notation I have, xn minus x naught divided by n. Okay, and I'll hit enter just so you can see it's a step size of 1, right? But what's it doing? It's xn, it's 5 minus -3. 5 minus -3 is 5 plus 3, 8, and n is 8. Alright, so we have a dx of 1. Okay, now you may be thinking, why didn't you just use the numbers? Well, because we're going to code this. We're going to make a what we call a function that will do this for any function that you come up with. Alright, so let's go up here to back over here. What do we do next? So once we've got everything, we do finally have everything now. We've got delta x, we've got our differential equation, we've got the initial point. We're ready to start doing Euler's method. Alright, so let's do the first one. The first value, x1. How do I get that? I start off with x naught and I add delta x. Okay, so again, I'm going to leave it open, but you could semicolon that if you don't want to see it, but there's the new x. Okay, how do I get the new y? Well, I start with the old y, I add to that the function evaluated, or the differential equation evaluated at the previous point, the x naught, y naught, and I multiply that by delta x. So I plug in the previous point into the differential equation, x naught, y naught, and let x naught, y naught, we've already seen what's going to happen there. X naught is -3, y naught is 1, and we've already seen when -3 and 1 go into f, we're going to get a tenth. So this is like a tenth. Alright, and then times delta x. So times, and we're calling delta x dx. Alright, so again, I can hit enter. You don't have to look at it to see it, but again, it started with that y equals 1. We already saw that this was a tenth, the differential equation. Since delta x is 1, we're just adding a tenth. Okay, now, the thing is, we've got a new point. We've got x1, we've got y1. What do we do to get x2? We do the same thing that we did to get x1. So I could literally, if I hit x on Octave and just hit up, there's how we got x1. Well, now I'm just going to change that to a 2 and that to a 1. Alright, and that's how we get x2, right? We just add delta x to x1, hit enter. Alright, and so we moved up again, -2 to -1. When I hit y, there was how I got y1. I'm going to change this to y2. I'm going to change this to y1, x1, y1, and there's the new y. Alright, and then you would just keep doing this every single time until you got to the x being 3. I'm sorry, 5. 5 is what we wanted it to be. So you would just keep this process going. Now, for those of you that have coded before, you probably see this is, since we're just doing the same thing, I'm just hitting up and changing the numbers. This is easily done with a for loop. So let's go through how I would code this with a for loop. So if I cleared this off, if I'm going to start all of it from scratch, I would still need, even if I'm going to do a for loop, I would still need an initial condition because I got to start somewhere. So I'm going to still go back to x naught. I'm going to hit up and hit that guy. I don't need to see it summarized, so I'm going to put the semicolon. Same thing with y naught. I don't need to see it. I would still need my final value in there, and I would still need to calculate delta x. I don't need to see it though. And then I need my differential equation. Alright, so there's my differential equation. I'm going to semicolon it off as well. I don't need to see it. So there's all I need to do it. Now, how does a for loop work? Well, let me define n. I need n to be defined. Alright, now we're ready to go into the loop. Well, there's one more thing I got to do. I'm going to build an x and a y array. So what that means is the very first thing that's going to go in the x array, this very first thing that's going in here for the x values is the first x naught. So to kind of visualize it, we're going to build an array of values, and it's going to start off with x naught, and then we're going to calculate a new one, and as it goes, as the for loop goes, it's going to do the next one. So that's the I plus 1 idea. So when I is 1, I plus 1 will be 2, and we'll be making the second value for x. Alright, and that's where we'll get the -2, and then it'll make the third one, and it'll get us -1. And it's going to build this for us as we go. We're not going to predefine it. We're going to let the for loop build it, and it's going to do that, with the chain of commands that we give it. And the same thing's going to happen with y's. We're going to start off, the very first thing in the y array is going to be the initial value of y, and then we're going to use a for loop to complete it and to build all of it. Okay, so again, this is where we're ready to do the for loop. We're going to create these two within a for loop. The x plus 1, the xi plus 1 equals xi plus delta x. That's going to be part of it. And then again, of course, this is going to be a part of it. So let's go back here and think about how we're going to code it. So the way we have to do it is for I equals, and we're going to start off with 1 because, again, that notation, if I is 1, I plus 1 would be 1 plus 1, which would be 2. The second x is a function of the first x. So we're going to start off with I being 1, and we're going to make it stop at n minus 1. So from I equals 1 to n minus 1, what are we going to do? We're going to say x sub. This is, you can't do a sub like a underscore. You just have to use the same notation we did up here. So the first x, the I plus 1x, is equal to the previous x, which is xi. So instead of using like subscripts, we're putting them in a parentheses, so it'll build our values within that array. So it's the old x plus what we call delta x up here, so dx for delta x. Alright, again, I don't want to see it. Tell you what, for this first one, we'll keep it open so we can see it, so you can see how the for loop is working. And then also the y, the new y coordinate, yi plus 1, that's equal to the old y, alright, plus the function, whatever you call this function. If you called it f, then use f. If you called it f prime, use f prime. Is the differential equation evaluated at the previous point. So xiy is the previous point. So we're going to put that in there, xi, comma, yi, and then times delta x. So that dx again. Alright, and that's how we get our new y coordinate. Alright, make sure you got all that closed off, semicolon, no, again, I do want to see it, so I'm going to leave it off. Alright, and then I'm going to tell it to end. Alright, and if you look at what's happening, we already have our x. Our first x is x naught y naught. That's the negative 3, 1. Alright, so for the first run of this for loop, when I is 1, it's doing 1 plus 1, which is 2. x2 equals the old x1 plus delta x. The old x, negative 3, plus delta x, which we saw was a tenth. So negative 3, or sorry, it was 1. Negative 3 plus 1 is negative 2. Alright, and then the y coordinate, the second y, when I is 1, the second y is the first y plus this stuff, which we saw as a tenth. So the first y, the second y. And then it's going from 1 to 2. Alright, so when it's 1 to 2, it's calculating x sub 2 plus 1, x sub 3. Y of 2 plus 1, y of 3. The third y, third x. And the fourth y, and the fifth y. Alright, and it says, when you don't put the semicolons on there and it does all these calculations, it gives you this kind of like, are you sure you're wanting to see all of this? So I'm going to hit F for forward just so you can see it keep going. So the first, the second, the third, the fourth, the fifth, the sixth, the seventh, we made it y8. So there's the last one. If I hit forward, it should just, give me the cursor. There's my last value. Let's see. 1. Oh, I'm sorry. That's how many steps I wanted. So I did need to go to n for this. I did need to go all the way to n since I started with 1. Let me go back into it real quick, and I'll just do 1 to n and just repeat all of it. So anyway, there it goes all the way to the last value, 5 and the 8.3. So I did need to make that go to n because I started with 1. So instead of 0 to n minus 1, we're going 1 to n. We want n steps. So 1 to n is n steps. 0 to n minus 1 would have been n steps as well. But we want to do 1 to n since we've got it written that way. Alright, so here's the thing. I want you to be able to write a program that does this, that takes in the function, the differential equation. It takes in the starting point, the stopping point, the number of steps we need, and we'll do this. So it can be user defined, it can be updated and changed, and it's not the same thing. So the way that we do this is in the editor, and we do these things called m files. So we're going to call this a function, and I'm just going to call it yn. The last y is a function of Euler's method. So I'm going to call my function Eulers. And what does Eulers take in? What do we need for Euler's method? We need an initial point, x naught, y naught. We need a final point, a final x coordinate. Alright, we need our differential equation, our f, and we need how many steps we want, how many steps we want to take to get from the beginning to the end. Right? Those are the things that we need to be able to do Euler's method. Okay, so once you're in here, you can use, like I could type in, once I'm done with this, I could just use this. I could type in Euler's, negative 3, 1, 5, define the differential equation, inline, or and then 8, whatever we want. But I also want to be able to, I like user interface. I like when you run a function, it asking you questions. That's just, if somebody walked in and didn't know how to use it, didn't know what to put in there, making it ask questions would make it to where that person could use it if they've never seen Euler's method before. So let's build it as if it's like a user interface. So the way we do that is we're going to ask for all these. So x naught equals, so the way I do this is I write input. That's a function, anything that's a built-in function of Octave will come up here. You can double click it, or you can just type it all the way out. Input. So I'm going to say, again, open parentheses, apostrophe, initial value of x, and I'll do a little colon, the space. I always put a space in there to give some space between the value that what I'm asking and wherever the user is going to put their answer. So the initial value of x, and we don't need to see it, so we put a semicolon. Y naught equals, same thing, input. What's the initial value of y? Semicolon. Alright, and so we'll do this for all of them, like the final value of x, the number of step size, and then we'll do something special when we get to f, so I'll kind of skip ahead to that. Alright, so for these last two, I just did the same thing. Input, what value of x would you like to estimate y? That's the whole point of Euler's methods, where, you know, move away from the initial point to a specific point where we want to figure out what y is, and then in how many steps between x naught, the first x and the last x. Alright, but now we're ready for a differential equation. So we're still going to do input. We're going to do something kind of different here. So I'm going to say that f is equal to input, same as before. What is the differential equation? And here I'm going to tell Octave that, okay, there's the end of what I want to ask, and then I'm put a little comma here, and I'm going to put an S there. What that does is that tells Octave that this is a string of what's being put in here. What somebody's writing in this block is a string of characters. It's not like a single individual number like the last ones have been. A number, a number, a number, a number. This is a string of values, and not to try to treat it as a number. Alright, so same thing, I'm going to semicolon it off, but right underneath here, I'm going to tell Octave, I always use little f and capital F. I'm going to tell Octave that change that input, what they put in there as a string, change it to an inline function. So we saw inline a little bit today, and I'm going to say inline, and f is the inline function. They're already putting it in here as a string. I'm just going to put it in there as a function. Okay, and then I'm going to semicolon that off again. I don't need to see it. Okay, so we got everything. We got our differential equation. We've got n, we've got our final point, we've got our initial point, our final x anyway. And now we want to build delta x and start building our array. So the first thing we need to do is to say, alright, what's delta x? Because we need that for the new x's and the new y's. So delta x is xn minus x naught divided by n. Again, I don't need to see that, so I'm going to hit semicolon. Alright, x1, again, we start our array. The first thing that's in there is x naught. The first thing that's in the y array that we're building is y naught. If you want to kind of go off of our, like the sheet that we made in class today that has the derivatives in there, you can actually keep track of the derivatives too if you wanted to. You could call it like, so this y, you could call it like yp, you know, for the derivatives, but you don't have to. You don't have to keep track of the derivatives unless you just want to. Okay, and then after we've got x naught and y naught defined, we are ready to define our for loop. Alright, so for I equals 1 to n, x sub, and remember we've got to do I plus 1 here, so I plus 1, the new x, equals the old x plus delta x. Okay, the new y, I plus 1, is equal to the old y plus, alright, how do we get it? Remember, we plug it into the differential equation. Now, notice I went from little f to big F. Okay, little f is a string of characters. It's not going to understand how to plug things into it. Big F is the inline function that we can plug things into, like I showed you before. So we're going to have to use big F here. Alright, and big F is, we're plugging in the x and y coordinates, the previous one, so just xi, yi. Alright, and then we multiply that guy times delta x. That's our new x, that's our new y. Alright, we can end that for loop. And then I would just have it display x and display y. That's how, let us see the values. Alright, I'm going to go up here and hit save. And then when I save it in the directory, I'm going to save it as the same thing that I put right here. Alright, you need to make sure those match. So I'm going to save it as Eulers. I'm going to hit save. Okay, and then when I go to the command window, this is what's nice about this. Clear this out. If I type in Eulers, it says what's the initial value of x. I can type in -3. Alright, what's the initial value of y? 1. Alright, for what value of x would you like to estimate y? I want to do it at 5. How many steps? We did 8 before. I'm going to update that. I'm going to show you that we can get better approximations. And what's the differential equation? The differential equation is y divided by 1 plus x squared. And there's x and y. There's 5, 8.3. Now here's the nice thing about it. That's all we've seen so far. Our x is moving up in this amount. Let's do Eulers. Initial value of x -3. Initial value of y 1. For what value of x would you like to estimate y? 5. Same thing. But how many steps you want to take? Well, this time let's double it. Let's take 16 steps. Okay, and then what's the differential equation? All right, and now this is x. There's that final x. There's that final y. So it's got a different value that it's estimated at. All right, here is the actual. Let me change that to like black or something. Here's the actual solution to that differential equation. We'll talk about how to do this very shortly, how to get this answer. But this is the actual solution to this differential equation. So there's the exact value that we're after. Well, the rounded version of the exact value on the actual curve. Remember, we're trying to live on this curve. We're trying to be all these points on the curve. But because our step size is so large, we are initially underestimating it. So initially I'm going to take that away. This was the first approximation we did with the step size of 1 are these red dots. And you can see we quickly got too low when it started turning really sharp like this, because we're riding it when it's lower, when it's increasing like this. We're going off on a tangent line for 1 whole unit when it's lower, and then we're going for 1 whole unit when it's lower. And so as soon as it starts bending up away from us, because we're staying on a shallower slope for longer than it did, than the actual curve did, it bends away from us. So that's why all these estimates are low, or lower, because of that really steep ascent that it took. And we basically got on these other parts of the slope field. When we made the step size I'm going to leave that on there actually. When we made the step size a little smaller, you can see that we kind of stay close to the curve a little longer, but still, because it's always increasing, and increasing the rate it's increasing initially, getting steeper as we go, because we're staying on tangent lines, we're staying on these flat lines, we're leaving that upward pull. So we're better. Our guess for the y value of 5 was way down here, and now it's up here. The smaller we make the step size, the closer we'll get to this actual value. Now, I'm going to go back to Octave over here, and you see, I've got 16 numbers on here. I don't want to keep, or 17 numbers on here. I don't want to keep doing that. I don't want to keep having to put this many values on here. So I'm not going to have it display x and y. All right, x, y, n. That's the final value we're after. So the goal of Euler's method is to give us this final value of y. So all I really need to do is define yn to be the final value of y in here. And remember, we're going from 1 to n. Alright, and it's doing n is going in there, n plus 1. So I'm going to put n plus 1. The final y, I know that looks weird, yn equals yn plus 1, but yn just means the final one. The reason why it's n plus 1 instead of n is because we call them x naught, y naught, and so the final one would be n units away from this, which would be n, but because in the array it's the x naught is x1 in the array, the nth thing would be the n plus 1 thing, because it's one bigger than the array, than the subscripts that we're using. But it's the last thing in there, and the last thing in there, because I is going from 1 to n, is 1, or I being n plus 1. So we're going to say yn is n plus 1, and that's all that we really want. We don't need to see all the x's and y's, we just want to be that last value of y. So I'm going to go back and say every time you see this little star, it means something's changed, so you need to save it if you've updated it. And then when I run Eulers again this time, again I'm going to clean it off so you can see it from the top. I can make n be really big here. I could take 100 steps in there. I don't have to see all 100 values. And our differential equation is the same it's been. And now since I'm not having to display x and y, it'll just give me that last value of y. So 13, and you can see that we're getting really close to it now. So it's 5 and 13, it's like right there. So we're getting a lot better estimates than we were, because we're taking teeny tiny little steps here, because of the fact that we're taking n being to be 100. So we're taking just teeny tiny steps, and you can keep decreasing the size of n as far down as you want to. Okay, so there's what we coded. There's ultimately what we want. This is like function notation. You know, y equals f parentheses x. Well, the parentheses in the parentheses are the inputs, and then the other side, the y equals, that's the output. So the output of Euler's method is that final y that we want to estimate.